My name is Amir Khandani. I work in the Electrical and Computer Engineering Department of the University of Waterloo, and I will present today a practical method to achieve perfect secrecy. What perfect secrecy means is that the message will remain absolutely secure in the presence of an eavesdropper who has access to an infinite number of received antennas for listening to the transmitted messages. Each of those receive antennas have infinite signal to noise ratio, so the eavesdropper will listen to the transmitted messages perfectly, and eavesdropper has infinite processing power to process the information towards possibly extracting the encrypted message. Perfect secrecy, also known as one-time pad, is based on bitwise XOR of a non-reusable binary key with the message. Here, X is the message that we would like to transmit, Z is the binary key which is composed of IID bits, and the length of Z is equal to the length of X, and at the transmitter side we perform the following computation, which is bit by bit addition modulo 2 of X plus the key is Y, and Y is transmitted. It's easy to verify that the mutual information between X and Y is 0, meaning that if an eavesdropper observed Y, will not be able to extract any information about X unless Z is known. Now, as mentioned, a key of size n can encrypt a message when n bits of data, and this key should be used only once. Otherwise, the dependencies that exist in the message, for example, English text, probability of different characters are different. If such a text is mixed with an key Z and the result is provided to an eavesdropper, this will enable the eavesdropper to extract some information about the Z, which means that if the same key is used again, it will not have that 100% security feature. This brings us to the problems of using this method. The first problem is that the content of the key should be communicated to both Alice and Bob. Alice and Bob are the legitimate parties. This is a procedure that is itself vulnerable to eavesdropping. And the second more important problem is to guarantee perfect secrecy. Each key should be used once and never again. Here we have a generalization of the concept of bitwise XOR to addition modulo 2 pi of phases, in the sense that if X is a phase modulated signal, for example a QPSK or an MPSK, Z is a phase uniformly distributed between 0 and 2 pi. Then when we add X and Z modulo 2 pi and transmit Y, the mutual information between X and Y will be 0, which essentially means that the eavesdropper will not be able to extract any information about X by receiving by listening to Y. As mentioned, the message X will be point of a PSK constellation, for example a QPSK. The key Z is a random angle with uniform distribution in 0 to 2 pi. So we have a set of IID phases uniformly distributed between 0 and 2 pi. And again, the mutual information equal to 0 means that the eavesdropper cannot extract any information about X, which is the original PSK constellation point, by observing Y. As we will see later, this operation of addition of phases modulo 2 pi occurs naturally as part of the transmission in a wireless channel, and this is one of the features that we would like to use to achieve perfect secrecy. Again, to continue with the notion of modulo 2 pi addition of phases as a generalization of bitwise XOR used in traditional cryptography, we go through some of the key points that enable us to use this feature and build a perfectly secure system. The first point is that the addition modulo 2 pi occurs naturally in wireless propagation, where X is the phase of the transmitted constellation point and Z is the channel phase. So you can consider Z as the channel phase to the eavesdropper, which is unknown to the eavesdropper. Consequently, when we transmit X, eavesdropper will receive X plus Z, and under certain conditions that will be discussed, will not be able to extract any useful information about X. The second point is that if Alice is one of the two legitimate parties, if Alice uses a 2 to the power of m PSK modulation to send m bits to Bob, this m bits will be hidden from the Eve, because the phase of the PSK constellation will be added with Z, where Z is the channel phase from the legitimate transmitter antenna to Eve's receive antenna. To further continue the discussion, we have the following procedure to use the features explained in the previous slides to achieve perfect secrecy. The procedure is as follows. First, Alice and Bob get access to a set of, say, n shared random phase values which are known only to the two of them. How we do this is something that will be discussed later. So there is a procedure that enables Alice and Bob to get access to a set of n phase values that are the same between them, and they are independent of each other, and each of them has an IID distribution between 0 to 2 pi. I said the phases will be the same, but in practice there will be small differences between these shared phase values due to the noise and other imperfections, but we will present a mechanism to account for those differences and correct them. Now, as I said, the shared phase values may have small errors from one party to the other one, but we can account for this and correct it. The second part is of this procedure, after such common phase values have been provided to the both parties, Alice, which acts as a master, generates a set of n PSK constellation. This n is the same n that we have here, is the number of shared phase values. Alice will generate n PSK constellation points with random data. For example, each QPSK can contain 2 bits of information, and these 2 bits are randomly generated by the master. Then the master rotates each of these PSK constellation with one of the shared phase values, and transmit the rotated PSK constellation point to Bob, who is acting as the slave. These bits that are randomly selected by Alice will be forming the key that is securely shared between Alice and Bob. The reason that we use those set of shared phase values to rotate the PSK constellation is because we would like to be able to correct for possible errors between shared phase values. Now, in the third stage, Bob, who knows the shared phase values or has his local understanding of the shared phase values, which may have small differences with the phase that Alice has used, will derotate the received PSK constellation with its own local understanding of the corresponding shared phase value and recover its data. So after this derotation, we will have a PSK constellation that has a slight rotation because of the possible mismatches between the shared phase values that Alice has used versus what Bob has used to derotate it, and also obviously in the process of transmission we have noise. Now, assuming that we have a 2 to the power of m PSK modulation used in this phase, and we have a forward error correcting of rate r. So the bits that are mapped by Alice to these PSK constellations pass through a forward error correcting code of rate r to enable subsequent error correction, which will correct the small phase mismatches in the original shared phase values, and also the noise that is present in the channel in the process of that transmission. So if the rate of the FEC is R, after detection, both units will have access to a secure key of size m, ym, because each PSK transmission had m bits of random data generated by Alice and sent to Bob, times n, because we have n shared phase values, and each shared phase value essentially was used to rotate and derotate one PSK transmission, and we have times r because we have forward error correction, and the effective rate will be r. So this many bits will be essentially error-free detected at Bob, and because Alice has originally generated those bits and encoded them, both parties will have access to that same random bit pattern, which will be used as a key. Now it remains to provide a mechanism for Alice and Bob to get access to this common or shared phase values, which is what we will discuss in the next slide. So as discussed, a major part of this whole process is a mechanism to generate a set of shared phase values that are IID uniform and known to only Alice and Bob. The following key points enable us to do this. Number one, wireless channel is reciprocal in the sense that the phase of the channel from Alice to Bob is the same as the phase of the channel from Bob to Alice. So if the two parties measure this phase on their own in their own receiver, they will measure the same phase, of course with some differences due to imperfections and noise. Now the question is that Alice and Bob, based on this reciprocity, will be able to measure one phase value, but we need many more phase values, and we need to make sure that in each of such measurements the channel to the eavesdropper has also changed, such that eavesdropper will, with each new listening, will have a new unknown, which is the phase to its new phase to its receive antenna. Now, how do we do this? First, dealing with the fact that we need many of such shared phase values. This can be done because the phase of a communication channel is composed of the phase from the transmit antenna, including the immediate neighborhood near field of the transmit antenna, to the receive antenna, immediate neighborhood and near field of the receive antenna. So if the RF characteristics of the environment in the neighborhood, close neighborhood of the transmit or receive antenna are perturbed, what it means that the properties are RF properties are changed. Then, although this perturbation is performed at close neighborhood of one of the antennas, its effect will change the entire channel, and its effect will be enhanced by multipath propagation, and the end effect is that the two parties will observe a totally new phase which has a uniform distribution between 0 to 2 pi. Now, as I mentioned, the variation due to the perturbation close to the transmit or receive antennas will be augmented by the multipath propagation of the RF signal as it travels from TX to RX. This means a small modification in the RF environment will cause a totally new phase. It remains to explain 2 points. One is how to perturb the RF environment and how to guarantee perfect secrecy. Because eavesdropper has a lot of antennas and will be listening to every transmission. The point is that we need to make sure in every exchange of a shared phase value between Alice and Bob, each legitimate antenna, which are antennas of Bob or antennas of Alice, is used only once. For this reason, we will deploy two antennas at each unit. Bob has two antennas. Alice also has two antennas. Each antenna of Alice and Bob can be used to transmit or to receive. Transmit or receive. Transmit or receive. Transmit or receive. Now, after the channel is perturbed, perturbing the channel will change all the phases from the legitimate units to the eavesdropper antennas, to every antenna of the eavesdropper. For example, phi 1, phi 2, phi 3, phi 4, which are the phases from antennas of TX1 and TX2 and TX1 and TX2 of Alice and Bob to this antenna of eavesdropper will change when we perturb the channel. Likewise, this phi prime 1, phi prime 2, phi prime 3, phi prime 4, which are the phases from the legitimate antennas to the another antenna of the eve, will also change. Now, the key point is that changing the channel state, so this RF perturbation, I also refer to it as changing the channel state, will also change the channel phase to each of the eaves receive antennas. So it will not only change the phase between the two legitimate parties, it will also change the phase to the receive antenna of the eavesdropper. And now, assuming Eve has a large number of antennas with high SNR for each antenna, what happens is that each of the Eve's antennas receives 4 signals. Why 4 signals? Because in the process of exchanging a shared phase value, each of these antennas is used once as a transmitter. So we have 4 transmission in total, and the key point is that each antenna of Alice and Bob is used only once in the process of exchanging a shared phase value. So when they are used only once, we will have essentially Eve will have 4 observation because 4 transmission have happened, but those 4 observations are through 4 new unknown phase values. And it's straightforward to show that when we have one observation XOR with an unknown phase, we get 0 information. When we have 4 observations, each of them XOR with a random phase, we get 0 information. So the same applies to every antenna of Eve. So every antenna of Eve will hear 4 transmissions, but will hear them through 4 new channel phase values to that particular antenna of Eve. With this introduction, now we are ready to explain one step of the steps used in exchanging those shared phase values. The slide here explains the steps taken after the channel has been perturbed, meaning that the RF environment close to antenna 1 of Alice, as well as antenna 2 of Alice, as well as antenna 1 of Bob, as well as antenna 2 of Bob is perturbed, and we are ready to generate a fresh new share phase value between Alice and Bob. To do this, at time t, Alice sends a signal, a preamble, a training sequence to Bob. It uses its first antenna. Alice uses her first antenna acting as transmit antenna to send the signal to Bob, and Bob will receive it with its second antenna acting as a receive antenna. This signal is internal to Bob, pass to the first antenna of Bob, which now acts as a transmit antenna. And Bob will forward the signal using its first antenna, which is acting as transmit antenna, to Alice, and Alice will listen to it using its second antenna, which is used as receive antenna. Now, if you look at this path that has been traversed, Alice, by comparing the phase of what was originally sent here with what was received finally, can measure the phase in this path. Note that to further enhance the security and the secrecy level, Alice can apply a random initial phase to that pilot signal that is sending and receiving finally at this point, and then comparing the phase between what was sent and what was received to measure the phase in this channel, in this path. Now, in the second phase, the channels remain the same, no perturbation. Now, the roles of the antennas are exchanged in the sense that in the first phase, Alice's first antenna was used to transmit, and its second antenna was used to receive. Bob's first antenna was used to transmit, and its second antenna was used to receive. In time t+1, these roles are exchanged, and the process starts with Bob using its second antenna, which now acts as a transmit antenna, to send a pilot, which is received by the first antenna of Alice, which now acts as a receive antenna. The signal passes internally to the second antenna of Alice, which now acts as a transmit antenna, and finally Alice sends this over the air to Bob, which is received by the first antenna of Bob, now acting as a receive antenna. The net outcome is that at time t, we measured this phase by passing the channel in this direction. In the second step, we measured this phase, which is essentially the same wireless path traverse in the opposite direction. So here we are moving this way. Here we are going through the same path in the opposite direction. Because of the reciprocity, the phases will be the same, and the other important point is that by doing this trick, by using two antennas and by changing the role of those antennas, each legitimate antenna is used to transmit only once. Consequently, in the total number of transmission, which is 4, when heard by Eve, it will hear 4 signals through 4 unknown phase, because each transmit antenna has an unknown phase to the Eve's receive antenna, and that transmit antenna is used once, so Eve will not be able to extract any useful information. So the conclusion, to just repeat the whole thing, we used each antenna to transmit once. This antenna transmitted at this point, this antenna transmitted at this time t, and then at time t plus 1 these two antennas transmitted, and the other two were receiving. Before explaining the further details of the steps involved in the key exchange, let us have a look at the actual hardware we have used to perturb the channel. This is essentially what I call an RF closure. It's a new design. It has not been reported in the literature. It's composed of walls. It has in particular 14 walls. Each wall, for example this one, has a piece that is solid metal on a PCB, and these small dots that you see are pin diodes. By a control circuit, we can turn these pin diodes on or off. So essentially the walls have a structure like this, in which all of the switches will be turned on or off. What happens is this structure will have a very interesting behavior, that in these two states of on and off, in one state it will reflect the signal back in, so this RF signal that goes and hits this wall backs in. In another state, the RF signal that hits this wall will move out, and it is as if the wall is transparent. So we have an RF mirror, an RF reflector, which is controllable. And again, this is a new design. It has not been reported something like this, that we have a reflector that can be controlled to either reflect or become transparent. Now we have this antenna in the center of this closure. This is a monopole, will have a donut shaped transmission pattern, antenna pattern. The signal will, and these walls, there are 14 of them, will be turned randomly by these control signals of 0 and 1 will be turned on or off, meaning that the signal will essentially either bounce back by hitting the wall, or will get through the wall as if the wall doesn't exist. Now it's easy to imagine that, for example, we can have a bounce back here, and then the signal can go this way if this is open. And by changing the pattern of on and off, we can have a variety of different ways of letting the RF signal to get out of this RF closure. Each of those bounces will have its own phase shift, and the signal will get out of the RF closure after the bounces through the walls that are transparent. So the signal will, after leaving this RF closure, depending on which wall it has got through, will go through a different path in the environment, and even the environment will augment the phase variation. So bottom line, here we have 14 walls, 14 mirrors, and we can, by controlling them with the switches being on and off, we can have 2 to the power of 14 channel state for each RF closure. So the best design for like a higher level of security is, as you recall, Alice and Bob each had 2 antennas. So we will use an RF closure like this for each antenna of Alice and each antenna of Bob. So in total we will have 4 antennas, each within its own RF closure, and this results in 2 to the power of 14 to the power of 4, a total of 2 to the power of 56 combinations to change the phase, which brings a lot of richness in our ability to generate randomness. Of course, this is not necessary. We can use one RF closure and put 2 antennas for each unit inside one RF closure. The RF closure, we have not tried hard to reduce its size, but because the interaction of these walls with the antenna involves near field effects, there is no strong argument to believe that the size of this closure cannot be made very small. It can essentially be turned into something quite small. We didn't spend time on adjusting the size because it was not of any significance to us. So here we have 4 examples for the antenna pattern corresponding to 4 different configuration of the on-off switches in that RF closure with 14 walls. As you see, changing the switch pattern has caused drastic changes in the antenna pattern, which essentially means that the phase observed at the other end will be totally different from one pattern to the other. Please also note that here antenna patterns are not used in the conventional sense of RF engineering to steer the beam and focus the energy. These are just essentially are to create randomness, and it doesn't matter the shape of the pattern. All what we want is that the patterns differ from each other such that each pattern will correspond to a new random phase. Now we come to point that we have all the ingredient to go one more time through the entire procedure for generating a key. We have 2 main steps. One is establishing the common phase values. This is achieved in these 3 steps. Step 1, perturb the channels at both Alice and Bob, in the sense that switch the RF closure to a new random state by using a random on-off arrangement for those RF mirrors. Step 2, after this is done, establish a common phase value using the method explained earlier, in which we use each antenna once to transmit, and we change the role of the antennas, and we traverse the path between Alice and Bob in the opposite direction. Once this is done, we have exchanged one shared phase value between them, and then we go to step 1 and continue until we have enough such common phase values, and the notation we used for this was n. Once this is completed, we come to the stage of generating the key. The reason that we do not use those phase values directly as key is that they will have small discrepancy between them, and we want to correct those errors, and at the end of the day convert the key, instead of a key based on phase, into a key based on bits that can be used in a conventional cryptography system which uses binary keys. Now, to generate the key after the common or shared phase values have been established between the legitimate parties, the master generates a set of m times n times 1 minus r. M was 2 to the power of m was the size of the PSK constellation that was rotated at the master and derotated at the slave. N is the number of phases that we have shared between master and slave, and R is the redundancy of the forward error correcting code. So we encode this using effect of rate R, and this results in m times n coded bits. This m times n coded bits are divided into segments of m bits. Each m of such bits are mapped to a point in a 2 to the power of m point PSK constellation, and each such PSK constellation is rotated by one of the common phase values. So we have n such PSK constellation, and we have n common shared phase values. Step 3, n such rotated PSK constellation points are transmitted from the master to the slave. Step 4, slave derotates the received constellation point by its local copy of the corresponding shared phase value, demodulates the derotated PSK constellation, and finally decodes the FIC to extract the random bits generated by the master. Those random bits will be the final binary key. And also, as mentioned, the rate of the FIC is adjusted to correct any initial phase discrepancies between the shared phase values, plus correcting errors that will occur because of the channel noise in the step of transmitting the rotated constellation from master to the slave. As mentioned before, each of the legitimate units, Alice and Bob, have 2 antennas, and they should be able to use either of these antennas as a transmit antenna or as a receive antenna. And this is a fairly easy task using a 2x2 crossbar RF switch, which will either connect the transmit path to this antenna and the receive path to the other one, or transmit path to this antenna, receive path to this one. As mentioned earlier, we have 2 options to use the antennas in the RF closures. To review this, let's look again at the method used to perturb the RF channel. As mentioned, Alice and Bob each have two antennas, where each of these two antennas can be used as a TX antenna or as an RX antenna, selectable through a 2x2 crossbar RF switch. This leaves us with two options. Option 1, at each unit, meaning Alice and Bob, the two antennas are surrounded by a set of walls which act as on-off RF mirrors, and we call this an RF closure. But the two antennas are within one RF closure. Consequently, if we use K mirrors in each of these RF closures, the total number of channel states will be 2 to the power of K for each node and 2 to the power of 2K as in combination of both of them. Option 2, which is a preferred option, is that each antenna at each unit has its own RF closure, meaning there are a total of 4 antennas within 4 RF closure, and 2 of these are at each node. In this case, if we use K mirrors to build each of the 4 RF closures, we obtain 2 to the power of K channel state corresponding to each of those RF closures, and 2 to the power of 4K in total. It will be the number of channel states. After the key is exchanged, there is a mechanism called privacy amplification, which is used in quantum key generation and in information theoretic approaches to generating a key based on common randomness. What it means is that if we have, let's say, 1,000 binary number, we can, through using a hashing function, we can condense those 1,000 bits into, let's say, 500 through a process which is deterministic, and the process itself, which can be considered simply as multiplying the 1,000 bit by a matrix, binary matrix of size 500 times 1,000, and multiplying the matrix modulo 2. The matrix is known to the eavesdropper, but the result of the multiplication of that matrix will convert a bit key that may have some redundancy, residual redundancy in it, and the size is 1,000, will convert it into a smaller key of size 500, which is more secure. So the privacy amplification is like multiplying a key of size p by a non-binary random matrix of size q times p, where p is larger than q. And this reduces the size of the key from p to q, but thereby reduces the effect of any residual dependencies that may exist in the final key. So this issue of privacy amplification, this is not the only way of doing it, and the reason I'm bringing this up is that like other methods to generate key or to share a key that can enhance performance by using privacy amplification, the same concept is obviously applicable here. Now, one final point remains to be explained. It's an outstanding question which may also appear as an outstanding concern that need to be addressed. The concern is the following, the question is the following. the whole point of one-time pad is that we have a key that we use it once, and if we use it twice, it's not as good as the first time. In this process of generating the key, if you recall, we started by providing the legitimate parties with a set of shared phased values. And then those shared phased values were like a key, were the initial key. But we use those to encrypt a bunch of binary numbers which were transferred from Alice to Bob, and those binary values form the finite binary key. The question is, if this process means that the key, the initial key, which are those shared phase values, have been used once, and the security in the sense of one-time pad is compromised. The answer is no, this is not the case, and let us see the reason. So again, to review, we use the shared phase values to encrypt a random stream of bits to be used as the final key. The reason we did it, we had two reasons. One was to remove initial mismatches between the shared phase values, correct for the channel errors, and also to convert it into bits, because we don't want phase to be used as key. Conventional system use bits as key. Now the question is, does this one-time use of the key, which are those shared phase values, contradicts the requirement that the key cannot be reused? And the answer is negative, because the source of degradation in the quality of the key comes from dependencies and probabilistic non-uniformity or dependencies that may exist in the message that we are encrypting. However, here the bits that we use to encrypt with those phase values were IID with information content of 1 bit per binary digit. This means that there was no structure, neither in terms of memory nor in terms of having non-equal probability in the message that we encrypted, and consequently the key, by being used once and the result being conveyed to the other party, does not lose its randomness feature. And this essentially brings my talk to end, and this completes my presentation. Thank you very much for listening, and if there are questions or comments, my email address is khandani@uwaterloo.ca, and the phone number is 519-885-1211, extension 35324. Thank you so much.